If you like our content, please like, subscribe, and click the notification bell to get alerts when we introduce new videos.
In this module, we're going to continue the introduction into IoT, and specifically now we're going to take a walk through some of the different technologies that are being used within IoT and look at both the pros and cons of those technologies, some other new technologies that are coming along, and also how to look at different vendor and device selection criteria as we start to look at how IoT can be deployed within a building or a facility. So one of the first things to look at when deciding on a sensor and sensor selection is the protocol. So there are a number of different protocols out there today that are being used specifically for IoT or have been modified from existing IT protocols and are still being used within an IoT arena. So the first one we can look at is Zigbee. Zigbee is a fairly well established protocol and technology. It's devised and developed specifically to provide a very good range and coverage within a building. It's a global standard that is built on the 2.4 gigahertz, which is a globally open frequency band for anybody to be able to be used. It also provides a good API and specification definition as part of the process for definition of the Zigbee standard. And it's also been, again, designed specifically from the ground up to provide a IoT type connection, which provides a very good battery life. So it's not uncommon to find Zigbee devices with extended battery lives of between 2 and 5 years based on normal uses. They also, as part of the upgrade and the revised Zigbee standard, now also support security. And by security we mean that there is the ability to encrypt and encode the data between the Zigbee endpoint and the hub that is forwarding and passing data. And again, one of the key things to look at with Zigbee is the total cost of ownership and the lower cost of deployment. Zigbee's been designed to be a low cost, cost competitive sensor deployment and operational costs accordingly. On the downside though, they can be fairly short range, especially as we get into a congested environment from a physical perspective versus a number of devices. You can also see quite a different range of quality when it comes to the endpoints or the devices themselves. You can see some very poor quality devices coming out of certain regions around the world. They also tend to be more of a consumer grade product rather than enterprise. This is changing. We are starting to see people now adopting Zigbee in an enterprise or in a more industrial application, but those tend to be more specialist products or designed and implemented for a very specific vertical where they've added or implemented additional features on top of the standard Zigbee specification. One of the big things really with Zigbee is the concept of clusters that Zigbee uses. Now, this is good because it clearly defines the capabilities of the device, but there is also a lot of scope in those clusters for vendor-specific applications. So it's very easy for somebody to build a standard compliant Zigbee device that uses standard Zigbee clusters and then throw in a couple of proprietary clusters in there, which means that most applications are unable to talk to it. And the other issue obviously is that this is in the 2.4 gigahertz spectrum, which is obviously very crowded. You have Wi-Fi in there, you have a whole load of other IoT radios and technologies that are in that 2.4 gigahertz range. Now we are starting to see a lot of movement from 2.4 as Wi-Fi is starting to move a lot more into the 5 and the 6 gigahertz range, but that 2.4 can still get quite congested. Other technology we have out there is things like LoRa. So LoRa is a fairly new standard. The nice thing about LoRa is it is a global standard from a protocol perspective. There are different issues regarding that global implementation of the standard. The nice thing is it's also very highly scalable. It's been designed and developed to allow tens of thousands of devices to all operate on the same network. It also provides extremely good battery life. So again, multiple year battery life is achievable with a LoRa sensor or LoRa network device. It's also highly secure. So again, the data is encrypted, encoded within the radio channel. The devices are encoded with vendor and manufacturer IDs and various other techniques to ensure that devices are not hijacked or moved on to other people's networks. Additionally, the LoRa network has been designed for very, very long range. So depending on the gateway or the LoRa access point that is being used, multiple miles of range can be achieved with very low powered battery devices and high gain receivers. And the nice thing is it's very simple with a very low capital investment for somebody to go along and to develop and install a LoRa network and actually deploy and operate it over quite a large area without having to spend tens or hundreds of thousands of pounds or dollars or euros to get that infrastructure installed and operating. Some of the downsides, unfortunately, with LoRa are it is a new technology. It's only been around for a few years in comparison to some of the other technologies. So that kind of means it hasn't really had a lot of the stressing, and the technology hasn't been used extensively really to get a lot of feedback and implementation improvements on the standard yet. The other thing is it really is limited on the number of silicon vendors that are out there that are manufacturing the chipsets for the devices and more importantly the gateways as well. The network itself is also very complex compared to some of the more traditional IoT networks. It requires multiple components and multiple interactions of those components together, from the LoRa network server to the gateway to the application servers. So it's a little bit more complicated for a lot of people to put together and to operate those type of networks. One of the bigger issues really though is the actual communication between the device and the application. With LoRa, it's very much designed on a vendor-specific payload. So and if you look at our modules specifically covering LoRa, you'll see we cover that in detail. But the key thing here is that every device could have a different payload, which makes it very difficult for somebody to write an application that is going to work with any type of sensor. The sensors themselves are growing in volume, but there is still fairly limited number of sensors out there when you compare it to other IoT protocols or networks that are available today. And it is really a very, very low data rate because of the range and because of the types of application and because of the battery life that it has been designed for a LoRa network. You see that the data rate itself is designed to be very low, a few bytes, and also you have shared time on the air, which means that you can't do anything like send large quantities of data, messages, or stream any kind of content. When we look at other technologies, things like Bluetooth, now obviously Bluetooth has been around for quite a while now, so it's really a very low cost solution. You start to see Bluetooth and specifically BLE now integrated into a lot of other chipsets and technologies. It's used extensively in different applications to ease onboarding, to speed the onboarding process of devices and technologies, and it's a very low cost silicon and an RF and implementation perspective. Very widely adopted, as I said, every mobile phone has it. Most cars and vehicles are now starting to implement BLE and Bluetooth technology. Headsets, handsets, all these kind of devices are all implementing BLE today. It does offer excellent battery life capability, maybe not quite as good as some of the other technologies like Zigbee and LoRa, but again, from a single lithium battery you can get multiple year life out of a BLE device depending on how often it's transmitting and its transmit power. And it has a lot of IoT use cases. So, we're seeing BLE being used in a lot of different applications for things like asset tracking, location-based services, but also as we start to expand and bring different newer classes of IoT devices, we're also seeing BLE being adopted in things like door locks or other types of sensors, environmental and telemetry type devices that can monitor large quantities of data and then transmit them using BLE. Because it's a very well known standard, very low cost, it's being very widely adopted in the market. And as I mentioned, we're seeing more and more people now starting to use BLE in their applications and within their devices to provide connectivity to mobile devices, but then also to use the BLE as the backhaul into the IoT network. And the nice thing about BLE is because it's a very well established standard, very well known, and there are multiple silicon vendors out there now implementing, using, and providing BLE technology and silicon. On the downside, though, one of the things is when we look at the number of sensors that are out there, there are a very limited number of them. So they are growing. We are seeing more and more adoption of BLE-based sensors, but in comparison to other radio technologies that are out there, it's still fairly small. One of the bigger issues is that the payload itself tends to be more proprietary. So the thing with BLE is that there are different ways that you can connect to it. So there are beacons that are transmitting, and again you can view our video on BLE specifically. There are beacons with payloads that are defined, iBeacon, Eddystone, URL, different types of beacons, payloads that are out there. But the actual formatting of the data in there can be proprietary and specifically coded. Additionally to that, to do anything more advanced, then you need to use what they call the GATT profile. The problem with the GATT profile is if you're a lock manufacturer who is building, an online door lock, you control all of the information in that GATT profile. So people can investigate and look at it, but all of the data is mapped into fields within that payload, which as the developer you understand, but anybody else looking in from the outside doesn't. So it really is very much a requirement for more complex devices to be working together with the back-end service or the network integrator and the device. Also, there's a new BLE standard which adds some new additional hardware capabilities which improve the usability of BLE. So it adds things like angle of arrival and time of arrival, which is very useful for location services. But the hardware can be quite expensive. You have to add some quite complex antenna arrays and some other different technologies onto the silicon and onto the design, which can increase the cost of the hardware implementation. So the technology has some great capabilities, but at the moment some of those additional capabilities have some quite high entry costs for developers or access point manufacturers. One of the key things though when we look at sensors isn't just the protocol. We need to start also looking at what other issues or considerations to have around sensor selection. So one of the first things to look at is power. And when we look at power, we need to think about, is the device mobile? Is it fixed? Is it a battery powered, or is it a mains AC, DC powered device? Now, if it's a battery, there are multiple different power technologies available within batteries, from lithium to nickel to cadmium to lithium poly. Now, all of these different types of battery technologies are available and commercially available and easily to source today. And the nice thing about batteries is it does have lots of different technologies that are out there depending on capacity, lifespan, environmental capabilities. These kind of things are all available by different types of battery technology. The other thing about batteries is they are cheap to both install, to run, and replace. So it's very easy to source multiple replacement batteries if the device is starting to fail because of a battery failure. They're easily available. The other thing is that they're very predictable. So you can very easily predict the life cycle of the battery with certain environmental conditions, with a certain transmit power and a refresh period. You can predict and model how long it is or how often you're going to need to replace the sensor within that, or the battery within that sensor. And it's a really important thing when people are looking at how to do a deployment. Is about, if you're going to be running on batteries, is how often does somebody have to go around and change those batteries during the course or the life cycle of the product. But unfortunately, the downside to that is that somebody has to go out and change that battery. So the replacement cost is much higher. So the actual physical cost of the battery is low, but the manual cost of going around and changing multiple batteries on multiple devices does have an incremental cost on the running costs of the solution. The other thing is the environmental impact. Some of these batteries are using rare earth metals that that has an environmental impact. These are not replaceable kind of metals, and as a result we need to think about those as part of the cost of the installation as we scale to billions of IoT devices around the world. These batteries are certainly something that we need to consider. The other thing is that they're not fit and forget. So once you've put the battery in, you can't just ignore that product now for the next 10 or 15 years. You do need to factor into the model and the handling of that device over the next period or 1, 3, 5 years of the life cycle of that product. When we look at other power opportunities we have wired. So we could either be AC mains powered, we could be PoE, we could AC to DC conversion. These are all options that are available to us. And obviously the advantage to that is that these provide us a very long product life. Anybody who's ever installed a thermostat into a building knows that once you've connected it, you've given it power, you basically can forget that for the entire life cycle of the building. Now, the advantage of the wired is that we do get this very long life cycle, and it really is very much a once you fit it, you can forget about it. But one of the key things to look at really is that you can also then start to add additional functions and capabilities into that device. So now you can have a multi-function sensor versus something that is maybe just providing temperature or humidity or one particular value on a 15-minute schedule. Because you have this power and this 24/7 operation, you can now start to add more capabilities into that sensor. You can also add in a higher refresh rate. Because you're not worried about the battery going flat, you can now get updates from that device much more frequently because you're not considering the power options quite so much. This also then gives you an increased performance and therefore a lower latency. So again, you're not having to wait maybe for a fixed time schedule before a device updates. You're not having to wait for other network considerations. Because you have the power 24/7, you can switch on, you can transmit, and you can shut down again very quickly. And again, because we're powered, we can also increase our transmit power. So we can have higher power, we can run longer range, we can have backlights if it's an LCD device. There's a whole load of advantages that we have by going to a wired environment. On the downside, though, is we do suffer from things like volatility. So if the power does go off, we tend to lose data. It's not predictable. So if the power goes out in the building, you lose everything. If the power goes out within a battery environment, the device is still able to continually monitor, gather telemetry, and when the power comes on and the network comes back up, it can upload that data. The installation cost is considerably higher as well. So, obviously now you're into running power cables, you have to chase out walls, you have to figure out a way of getting the power to that device as a result. That additionally can have additional costs around safety. So, if your device is a higher voltage, mains voltage device, that has additional safety certifications and safety costs associated with it. You're now running higher voltage cables, which means that you need to deal with, different safety and insulation and conduit running for those cables. So, and additionally, because they tend to be higher power, multifunction, they tend to have a higher running cost as well. So the batteries have a cost that's predictable, but unfortunately things like a thermostat or something that's running off a mains power will have a mains power supply which isn't as efficient, and therefore you'll generally tend to have a higher running cost for that device. Then on top of that, there are other power technologies out there as well. So we have environmental powered devices. So these might be running off of thermal differential, they might be piezoelectric, or they may actually be wirelessly driven, wirelessly charging or wirelessly powered devices. Now these have a lot of very good advantages. One of them is that obviously you don't have a battery. So the device itself is gathering or generating, harvesting electricity from different types of differential voltages or piezoelectric energy charging or even wirelessly connecting. Now that obviously that has some advantages. The other thing is that there is no wires, there are no battery costs. You have the advantage of minimal installation costs where you can literally just stick it to the wall and you don't have any additional costs or battery disposal costs or power supply issues. These tend to have a very low initial cost as well as kind of no maintenance or running costs associated with them because of their harvesting capabilities. On the downside, though, these are all relatively new technology. These tend to be very, very low power devices. They don't tend to offer multiple capabilities, and they tend to currently be from one or two vendors as well. So they're both a combination of newer technologies with limited vendors and limited capabilities. So what you're seeing is a kind of a hybrid approach where maybe they're generally running in piezoelectric, but they maybe have a battery backup so that you extend the battery life, but you still have a lot of the capabilities. They also tend not to be using any of the more standard protocols, obviously because they are using very low power, and some of the radio technologies out there today that we've talked about tend to be designed to run off a battery. They tend to have a slightly higher power. So what you'll see is that the RF standards maybe are more proprietary or are using a lower frequency so that they don't have to use some of the more complex modulations. What we're also seeing is they tend to be more action initiated. So what does that mean? Well, what it means is that you have to do something to the sensor before it will send an update. So it could be a door contact sensor that initiates a transmission. Now that means that you can't poll it, you can't find its status, its query. You also get no network status statistics or information about what's going on. So you don't know if that device has a good connection between the sensor and the hub until it needs to send a message. So that makes it very difficult to plan and monitor your network in a realistic manner and figure out what's going on within the network. So what are the other considerations that we need to think about when we're looking at sensor selection? So there are other technologies out there. So technologies like Z-Wave have been around for quite a long time now. One of the key things with Z-Wave is it's really aimed at the consumer market. We don't see a lot of enterprise grade Z-Wave products, but the nice thing is there are a lot of devices that are out there in the market and commonly available. Ethernet is another technology. It's very, very prolific. It's out there. It's very easy. It's very well understood. There's a lot of people that are developing solutions and sensors based on Ethernet. Again, Wi-Fi, similar approach effectively to Ethernet. It tends to be an IP-based network. It's very versatile, allows a lot of placement. But at the end of the day, you still need to provide power to these kind of devices if you're going to run them for long periods of time. But it is a very versatile, very well understood technology. There's also technology for something like called an Ocean. Now, it's a new technology, kind of a single vendor. There is an Ocean alliance, and they're defining how they can make it better. It uses the sub gigahertz frequency range as well, but it's an interesting one that's certainly worth keeping an eye on going forward. And then there's also Zigbee low power. So the Zigbee alliance have looked at the Zigbee protocol and said, well, how can we make it work in an even better lower power mode? So there's some interesting things going on with Zigbee to get to this much lower power and more long life battery capabilities. When you're looking at sensors though, but you also need to look at the vendor that is providing that sensor. So you need to look at both, build quality. Is it a consumer grade, an enterprise grade, or a medical grade sensor? Because that will have quite a big impact on the duration, life cycle, and reliability of that sensor, as well as the quality of the readings that you can expect from that device. Again, you also need to look at things like supply continuity. Is the manufacturer going to build 2 or 3 runs and then obsolete the product? Do they have good capability for version control policy? So, if you buy a batch today, is the batch that you buy in a year's time going to be the same? Is it going to be a different version of silicon, software, lower quality components, higher quality, different costs? All of these things all need to be considered when you're looking at sensors and various things like that. Exchange rates is also something else to look at. When you look at a cost of a sensor, are you factoring in the extra fluctuation in exchange rates? And then the other thing really is continuity of supply. So as I mentioned, we have supply continuity, but it's really about making sure that not only from a sensor perspective, but also at a silicon vendor, are there multiple silicon vendors producing that chipset or producing a chipset that can produce your product that you're looking for? Do they have a good end of life policy and a capability to continue to manufacture this for the duration of your project and your application? And then on top of that, we also have to think about, don't just focus on the action, the event, the device capability from a sensor perspective. Think about other functions and capabilities that we want within that device. So, a door sensor, for example, great. So it tells you when the door is open or closed. But it would be useful also to know if somebody's tampered with that door sensor. If you're putting that device into a mission critical environment and your business is reliant on knowing if that door is open or closed, you probably ought to start thinking about making sure you have tamper alarm capability to detect if somebody has manipulated it. Additionally, you need to think about battery and power monitoring. So again, if it's a mission critical system, you need to know that the battery is good and operating when you're working remotely or you're away from that device. Good signal quality reporting is also important to make sure that you know the performance of the signal between the device and the hub. And that doesn't just mean signal strength, that also means bit errors or any other kind of quality indications between the two devices. The ability to look at the time last seen. So is there a heartbeat coming from the sensor? Is it telling you that it's alive versus it going to sleep for very extended long periods of times? You have no idea if that device is still alive or if that device has failed in some certain aspects. And also thinking about things like multiple function sensors. We're starting to see already the migration within IoT sensors away from it just being a single functionality. So it's not just a door sensor. Now it's a door sensor with environmental capabilities, with tamper alarm, with battery monitoring. Other capabilities are starting to be built into the same sensor. So you're able to build a better view of your environment from a single device. And then the other thing to think about is how easy is the device to onboard, to pair, to bring into your network. What about the discovery process, the provisioning, maybe firmware upgrades over the air is something you need or you need to consider. Security management, authentication, and then the ability to hack those sensors within different environments. You need to consider all of these as part of the system and sensor selection protocol. So when we look at sensor connectivity, and you have to start thinking about the different ways that you use sensors within your environment. And that includes a lot of different things. So the first thing to think about is polling versus pushing of events. Polling means you are talking, you are asking the sensor, are you open or closed, or what is your current status on a predefined period. The downside to that is it's very inefficient, but also it might have an impact on the battery life of the device. Pushed events means the device will only send you an update if there's a change. Sounds great, but that can also have downsides with regards to network stability and overview. Additionally to that, we also need to think about the overall network traffic. So the more devices we add, then you have more API calls, more radio frequency, more RF communication, more network traffic is all going on, which explodes exponentially. The more devices you add, the more network traffic that's being generated, which has a huge impact on your time on the air and all of the impacts around network band plan and network design. Then on top of that, we have to think about the system workload. So we want to build an efficient, tight IoT network. As you add in more different types of devices and traffic and management entities on top of that, that can include impact on our CPU load, the amount of memory we need, our network traffic, and it increases our overall power demand within our IoT network. Then we have to think about the battery requirement itself. As the more events are going on within our network, that has a direct impact on our battery life, and that could have bring it down from weeks down to, from years down to weeks of endpoint capability. You also need to think about the sleep schedules on some of these devices. A lot of the way that the IoT devices work and become very battery efficient is they sleep for 90 to 95% of their time. So if there's nothing going on, they are asleep, they're not transmitting, there's no processor running, everything is really shut down. That has an impact on latency and as well as battery life. And you also need to think about how the system might be built across multiple sites. So, a lot of the times when we think about IoT, we're thinking about a room or a building. Well, what happens if you need to build that across multiple sites? How does that impact the sensor connectivity, the sensor network, and how the system all communicates with each other? And the next thing we need to think about, or the last thing we really need to think about is network scalability. So how do you scale from one device to tens of thousands of devices? How many gateways or access points do you need? And your controller, how do you provide additional redundancy and scalability within that? So one of the key things to look at is the controller density. So you have an IoT controller, but do you have a backup controller? So we call it N+1. So it's the ability so that if one of the controllers goes down, the other one can take over the function, so your IoT network doesn't go down. And you make sure that those two are constantly synchronized and up to date between each other. You also need to think about the gateway density. How many gateways can one IoT controller handle? So, in the RUCKUS IoT suite, we can actually have 500 access points or IoT gateways connected to a single IoT controller with N+1 master slave capability, and we can have multiple controllers within the same environment. Then on top of that, how many endpoints, how many Zigbee or BLE or how many devices can be connected onto a single gateway? So depending on the application, you might want to change that. So it could be anywhere between 16 or 32 devices, depending on the type of devices that are being used. Now that obviously gives you a scalability. So you need to look at your building or your environment and say, well, how many devices do I need to put onto my network? And then how many gateways do I need? And then how many controllers do I need? So, with a single setup of one controller with an N+1 and multiple gateways, 500 gateways with 32, that gives you kind of the average somewhere between 16 and 32,000 endpoints per network. And then you have to think about the same thing about what protocols you're running. So we talk here a little bit about Zigbee, but if we're running BLE, that will have a different scaling factor. So, if we want to use our access points as beacons, and we're using it for beacon as a service, that might give us somewhere in the order around about 400 BLE beacon packets per second. So we're able to transmit depending on our refresh rate of our beacons, up to 400 BLE packets. So if we had 100 beacons, we could have 4 beacons per second per beacon. If we had 400, then each one would be 1. And then we also need to think about if we are doing location services and we're looking at how many devices are around an access point, we need to think about how many we can reliably detect within a network or within the close proximity of an access point, and that needs to be somewhere in the order of around about 125 beacons per access point. Now there are some dependencies depending on beacon frequency, and in other words how often the beacon is transmitting, and the distance from the beacons to, and some various other parameters, but these are all issues and numbers that need to be thought about when you're starting to architect and design a network to be deployed into a real world environment. So that completes our insight and overview into the IoT 101 technologies, and specifically now we've looked at how we can verify and start to specify different sensors and networking protocols that we might want to use within our IoT network.